And as usual, we would like to thank the library and the Library Foundation for making this possible. And hopefully we'll be able to return to the library in the not too distant future as vaccines are really ramping up in Teton County, which is wonderful. And please do remember the Library Foundation and your philanthropic gifts at Old Bill's time. Now I'm really pleased to introduce Dr. Joel Pederson, I'm sorry. Dr. Pederson is the professor and head of the department at Utah State University, and his research and teaching interests are in geomorphology and landscape evolution. He applies fieldwork, geochronology, and terrain metrics to investigate landscape responses to tectonics and climate change and to decipher the landscape evolution of the interior West. He's originally from rural Minnesota, but he made the pilgrimage to the Southwest for graduate study, and then feels very fortunate that he got a job here at Utah State. So he's been at Utah State since 1999, first as assistant professor, and then has worked his way up through undergrad director, grad director, associate professor, and now he's the head of the department. In addition to that, he's teaching 2 courses, physical geology and advanced tectonics, or geomorphology, or advanced tectonic geomorphology. And he is also married to Carol Deller, who is a professor of geology at Utah State, and they have a son named Zane. So with that, Dr. Pederson is going to talk to us about the formation and history of our very own Alpine Canyon right next door. So thank you for that, and we look forward to your talk.
Thank you, Cynthia. I really appreciate everybody joining us, and I appreciate this group's resilience in holding talks over Zoom and getting used to that. I do hope that that my talk addresses the main title here. I'm going to share my screen and get the slideshow going, and I'm going to get my laser pointer going. All right. I want to point out halfway through my talk, I hope it's okay. I plan to stop and pause and give people a break, and also answer any questions you might have early on in the talk. And so not only at the very end, but also midway through, I hope we can pause. And so if you have any questions about the research questions I'm asking or the methods I'm using, I hope you'll go ahead and chat, put your questions in the chat right away, because we'll take a break midway through and answer some questions. Okay, so I bet many of you enjoy driving or kayaking or rafting through Alpine Canyon between Hoback Junction and Alpine, Wyoming. And to some degree, the study is focused on that, and I'll address these questions about its history. Also, I want to point out that this presentation is really distilled from a paper which is in press at the Geological Society of America Bulletin. And the longer title of that paper is Patterns of Incision and Tectonic Deformation on the Flank of the Yellowstone Hotspot, using terraces and topography. And so that's really what this talk is going to be about. But also, I can only talk about a fraction of what is in this paper. My co-authors are a former graduate student, Daphne Tuzlak, down here, a former postdoctoral researcher, Aaron Buffa, and then my colleague, Tammy Rittenauer, is a geomorphologist here in our department at Utah State University, and she directs our luminescence geochronology lab. And you'll see that that method of numerical dating is important for this study. Okay. All right, so taking a step back for background, I know that many of you know about the geologic story of the Yellowstone region better than I do. And it's a real hotspot of inquiry in the geosciences, thinking about big scale tectonics and even small scale tectonics. So Yellowstone, of course, is world famous as a huge mega volcano and supervolcano. And there are geodetic studies at very short terms that have documented that, in our historic times, there's a great deal of surface deformation, areas that are uplifting and areas that are down dropping right around the hotspot at rates that are centimeters per year. And so I'm sure you guys are familiar with those studies. Also, there's a whole host of high profile studies and debates about the hotspot at a grander scale and its origin and its geologic history. And one of the things that I find intriguing are numerical modeling results from geophysicists that give us a view of what the Yellowstone hotspot is doing to present day topography. And so in this example, I want to just focus in on this lower right diagram. This is an example from a paper in Nature not too long ago, where they take a numerical model that involves mantle and crustal dynamics, and they run it forward a step in time to get at what the sort of present day rates of uplift or the rates of dynamic topography are. So if you can see, this is the Western US, and here's this sort of tooth-shaped or kind of crescent-shaped area of topographic support. And right over the Yellowstone hotspot, there are places where there's a kilometer or two of excess topography or height in the landscape that is being held up by mantle motion and heat flux. And so we know that in our present day world, if we look at a snapshot of present day time, that this supervolcano is seething and deforming, and also that this supervolcano is actually holding up high topography across the region. So that's sort of at a present day snapshot. I want to take a step back now and think about long geologic timescales. And so you folks all are familiar, I'm sure, with the geologic evidence for the history of the Yellowstone hotspot and the linked Snake River Plain, right? Whereas the North American plate has moved over the hotspot, it has left behind this sequence of big volcanic centers that go from older to younger across the Snake River Plain towards Yellowstone. And that the Snake River Plain itself is sort of the tectonic damage zone that is subsiding in the wake of this passing hotspot. Okay, so let's see what I've forgotten here. So there's all of this geologic evidence from many lines of inquiry. And one of them is that people have identified this parabolic shape where there is high topography along this crest or this crescent shape. And this is also where active normal faults and extension are aligned. I want to point here, I have a label here, the Yellowstone Crescent of High Terrain. This dashed red line marks a hypothetical crest of uplifted terrain being supported by that hotspot today. And so I'll bring up this hypothetical sort of arch of an uplifted area here in a minute. So let's see if I've covered everything here. In general, the geologic model, of course, is that with this plate motion in the hotspot, we've seen over 15 million years, a migrating wave of magmatism, of a sort of bow wave of uplift, extension, and then subsidence in the wake behind it. The crest of the Yellowstone highlands versus the Snake River Plain represent over a kilometer of topographic relief between this area that is hypothetically uplifting and this area that is subsiding. And one thing that does is that terrain and that gradient moves through the landscape. It has changed the drainage systems. And through stream piracy and capture, the Snake River system here has essentially been lengthened as this hotspot marches through North America. I have down here, I don't want to get into it too much, a study that focuses on how drainages over geologic time have been redirected and captured into the greater Snake River system in this subsiding area. So we have data from the present day, and we have this really well-developed conceptual model of the Yellowstone hotspot over 10 million years of geologic time. And so I'm going to sort of claim that there's sort of a missing in between set of data that is really critical. Now, there are plenty of quaternary studies in the Yellowstone region, but there's not many that are focused on tectonic geomorphology, and not studies that are at the sort of quaternary timescale that are addressing the questions that these big models are bringing up. So I say here, the missing evidence here is that we're missing measurements that are at the intermediate or quaternary timescale that can fill in that gap between the present day observations and these grand geologic models, and actually sort of test this story, right? If we think that this crest is uplifting and this area is down dropping, well, what are the rates of that? And do we see that in the landscape? And so that's what I would like to try to get at, and I'm trying to peck away at this hole in our data set. Okay, this up here reminding me that there have definitely been studies done along rivers on the sort of leading edge of Yellowstone here in the Wind River, of course, in the Shoshone River, leading into the Bighorn Basin. And these are studies that I'll bring up again later that have tried to use these river systems and how their histories are recorded in river terraces to try to get at what's uplifting and what's not and what the rates might be. And we're going to do the same thing here along the Snake and Hoback River. Okay, so this is just an enlargement and zooming in. I'm going to just point out the study area that we're talking about is Alpine Canyon. Of course, you folks are in Jackson here. And I'm going to focus on part of the Hoback River that has its confluence at Hoback Junction, and then joins and goes through Alpine Canyon. And then, of course, the Snake River continues through Swan Valley. And I have a last slide with a little bit of new info from the South Fork Canyon along the Snake. But if you look at this, what I'm trying to do is I'm trying to set up a transect along this river that goes from this hypothetically uplifting area to this area that is supposed to be subsiding. And so if we look along this river and we look at the river's history, do we see the effects of this uplift and this subsidence? Okay, so this is a diagram, a longitudinal profile, and there's a lot on this diagram. And so I want to point out that these blue lines are the river systems going from higher elevations upstream and flowing to the west and dropping as they go downstream. All right, and so this is my study transect where we're following the Hoback River going to the west, going through Hoback Canyon to where it joins the Snake River at Hoback Junction. And then that's where Alpine Canyon begins. And the steep part of Alpine Canyon is here where the whitewater daily section is. And then, as you guys know, the part of the Snake River here is buried under Palisades Reservoir, excuse me. And then the Snake River reappears and goes through the South Fork Canyon and enters the Snake River Plain. So as we go from this stream transect, we're going from this area where there might be uplift along this Yellowstone crescent of high terrain to this area where there's subsidence or dropping in the Snake River Plain. And then these red dots are places that we're going to visit and go study. And then especially this student, Daphne Tuzlak, did quite an intense study right here in Alpine Canyon. So most of what I'm going to show you is focused right here in Alpine Canyon, upstream of the Palisade Reservoir. Okay, so here's a conceptual model that I hope we can get in our minds and as something to try to test. If we're looking along a river profile from upstream to downstream, going from upstream to downstream, then here's some different possibilities of patterns we might see if we can look at river terraces. So I think my next slide shows you some river terraces and how we use them in case folks aren't super familiar with that. But in general, if we had a record where we could look at where the river was and what its elevation was, let's say 100,000 years ago, and we saw different patterns with that, we could use it to test what's uplifting and what's subsiding and what is controlling the profile of the river. So for example, if here's a simple river and it's mostly responding to uplift upstream, then we would see that if we look at the history of the river in an old terrace, that old long profile would actually be sort of converging downstream relative to the modern profile, because these old markers are getting uplifted differentially by the Yellowstone crescent of high terrain. If Snake River subsidence downstream is the main source of base level fall driving incision in the landscape, then we would see that the greatest incision might be downstream rather than upstream, and that incision has tried to propagate upstream through a series of nick points, and that there might be an upper part of this drainage system that hasn't really seen this base level fall all the way down here. So these two patterns are kind of the opposite of each other. This has downstream converging terraces, whereas this might have terraces that are actually diverging downstream towards where the base level is falling. Finally, there is an important intermediate here, and that is that along a river through its history, the old markers of where that river used to be might be broken up by active faulting. And so most of you are familiar with, of course, our region is an area where there are active normal faults. And those active normal faults slip through time, and they can move and offset these terrace markers. So here's three distinct patterns that we can use terraces to sort of see how they're deformed and try to test what about tectonics is controlling the incision in this landscape. Okay, I'll show you some pictures, of course, from Alpine Canyon, but I wanted to give an example that's really clear, I think, from a study in the Colorado Plateau, which is where I've done most of my research. So I hope this is clear. These are some students doing some surveying, and we're looking across the Colorado Plateau Desert at a fault contact between Jurassic and Cretaceous rocks. But going right across this fault is the base of a Green River gravel. So this is the Green River near Green River, Utah. And this M6Y, this is my designation for a river gravel that we'll see dates to about 100,000 years old. So here's a 100,000-year-old river deposit. And 100,000 years ago, the river was up at this elevation, planing off this erosion surface and leaving behind gravels from its bed. And we can see that since the river left this place, we can tell that this fault has not moved, right? Because it does not penetrate or offset or create a fault scarp on this nice flat river terrace landform. Okay, so this Little Grand Wash Fault in the Central Colorado Plateau has not been active in the late Quaternary based on evidence from this terrace marker. So we're going to try to do things like that and look at where things are offset or not with these markers. So here's the example from here of another way of using all of these terraces to get at this sort of information. So here's a cross-sectional diagram where this M6 here has got numerical ages of about 100,000 years old. But then in the landscape, inset below that, there are multiple gravels that mark the history of the river through time. So as this river has down-dropped and incised through the landscape in Utah, it leaves behind little markers of different ages, getting younger and younger as it goes to the modern day. If we have a record like this through time, we can calculate incision rates, right? And so the thing I'll report to you is incision rates in Alpine Canyon. And I wish I could say that we had multiple, we have all these beautiful terraces in the Colorado Plateau, but we have less to work with in Alpine Canyon, but we still can give you an incision rate. Okay, so there's an example of rivers used to see whether there is tectonic deformation and to get at incision rates. I think I'm going to go through this kind of rapidly. I have a slide here. I want to talk about luminescence dating, right? The data that I'm going to show you relate to optically stimulated luminescence dating. And the lab we have here at Utah State University is actually mostly in a dark room. So this is a photo of a student working in this dark room lab to process sediment and can conduct one of these ages. So I'm sure many of you know what luminescence dating is in general. And I have this kind of embarrassingly simple cartoon that's just in 2 steps. With luminescence dating, we're zooming in and we're looking at individual grains that are sand in size of quartz and feldspar minerals. Right, so quartz and feldspar are very common at Earth's surface. And luckily, one of the things that happens in these, in the molecular structure of quartz and feldspar is that when they're subject, sorry, my animations are going on their own. When they're subject to uranium and potassium and just radiation in the sedimentary environment that they're buried in, they get dosed by radiation, right? And that radioactivity in among the sediments actually can occasionally take an electron and bump it up to a higher orbital state in the crystal lattice and the molecular structure. Through time, as sediment is buried, this dosing by radioactivity continues at a predictable rate. And these electrons that are in higher traps get accumulated over time, and it creates this signal of how long the grains have been buried. Then, if these buried grains are subject to some energy source, whether it's thermal energy or whether it's optical or solar energy, then those photons of energy, in the case of the sun, can actually hit these electrons, give them, impart enough energy so that they pop out of their higher orbitals. And when they go back to their regular orbital state, they luminesce a little bit. All right, so luminescence dating takes advantage of this system of storing this signal over a length of burial time. And then in the laboratory, we can subject it to controlled light and actually measure how much of this luminescence is given off, which is a function of how long that was under the ground getting this radiation damage. Okay, so the take home here is luminescence dating utilizes quartz and feldspar sediment from like stream alluvium, for example. And it gives us an amount of time that that sediment has been buried away in deposition. And so it's a burial date. It's very, very useful. Okay, so here is a really beautiful river terrace and a deposit along the lower Hoback River flowing towards Hoback Junction, just around the corner. So maybe you guys can picture where this is. This is on the way up to Camp Davis, if you're hanging a left at Hoback Junction. If you look over here, the terminology here, there's Cretaceous bedrock, and then there's a pile of gravel forming this alluvial terrace landform. And the basal contact of this is called a strath. And the top of it is called a tread of this landform. And if we scramble up onto the Cretaceous bedrock and we can find some sand grains that we can sample, we can get a luminescence age of how long ago the river deposited that sediment there and buried it. And so one thing that's really common is that in this particular terrace, which I'm going to call terrace number 2, we get ages that are as old as about 25,000 years ago. And in the upper parts of the deposit, we get ages that are about 15 or 13,000 years ago. All right, so the river was up here at this elevation rather than down here, between 25 and 15,000 years ago, sweeping back and forth and leaving behind its bed sediment for us to come by later and numerically date. All right, so this is a beautiful marker that we have an age for, and it can tell us all kinds of information. And so this study and this paper that I'm trying to present the results of is based on about a dozen or 15 of these luminescence ages. And so this table is no fun to look at. It's just reminding me that this is a primary data set of ages going from young to as old as about 100,000 years that we can use to interrogate the terraces in this landscape and try to understand about tectonics. So I want to pause for a second. I am halfway through this presentation, halfway through the slides. And I just wanted to stop and take a break, take a drink of water, make sure everybody is still awake, and see if anybody has any questions so far. And I'm worried because I see that the chat has no questions in it.
Say, Joel?
Yeah.
Let's see. So let me, am I unmuted?
Yep, we can hear you.
Okay. They're actually, okay, let me start my video. There actually are just a couple of questions. And on that last slide, one of the questions is, why are the younger terraces above the older in Hoback? You showed a couple different models, and I guess at least one of them would be, you'd have the older terraces above the younger ones. So what's the implication there?
Well, that's interesting. Now, I don't know how, did I actually show a slide of that? There is, I will show a slide where there is some complicated relations between these terraces, specifically just downstream from Hoback Junction. But in general, I think, yeah, the intuition is correct, right? In an eroding landscape, we should find older markers higher in the landscape, and then a history of the river leaving behind younger and younger gravels as you go down. So, one of my next slides is going to be getting into the details of the stratigraphy of these terraces we see. And hopefully I'll address the question of how, how do these things work in real life.
Okay, another one is, what's the range of accuracy on the dating there like that? It looks like it's very specific. I'm sure it's not. So, what are the challenge? How much, what's the range in uncertainty, and what are the real challenges then in dating, making dates like that?
Okay, yeah. Luminescence dating is a little bit distinctive, I think. It is, first of all, it's specifically something useful to quaternary geologists, right? The total age range that luminescence dating can go back is really only a few 100,000 years. So if you're talking about things that are 1 million or 2 million years old, usually luminescence dating is no good for you. It's sort of like radiocarbon dating in that way, although it can go a little bit farther back in time than radiocarbon dating. The question was asking about its sort of precision. And one other thing about luminescence dating is that in general, the luminescence dates that I'm going to show you, for example, they actually have a little bit bigger error bars than most geochronology these days, right? And so if we looked at that table more, you would find that I might report an age of 40,000 years old, plus or minus 8,000 years. And so actually we're talking about error bars that can be 10 or even 20% of the numeric age, the central age. And other geologists work on older systems, for example, uranium lead dating in zircons that is, extraordinarily precise. Their precision is orders of magnitude better than luminescence dating. So I'm going to admit, actually, one of the things about luminescence dating is one of the drawbacks of it is that it's actually a relatively imprecise tool. But its advantages are really great. Because quartz is everywhere in the landscape, it has many, many uses. And also the luminescence ages are relatively easy to sample, process, and generate. So even though an individual age might have relatively large error bars for a scientist, one of the advantages of luminescence dating is you can use it almost everywhere. And you can get multiple ages, right? You can get 20 ages. And when you have 20 relatively sloppy ages, they can converge statistically into something that's very, very meaningful.
Okay, another question about the technique is, how long has this technique been available? Luminescence dating.
There's a two-sided thing. Luminescence dating, broadly speaking, has been around a long time. And I bet you a lot of you have heard of thermal luminescence dating. Thermal luminescence dating was used heavily with archaeology and other studies for decades. And then the short story is that about 20 years ago, there were some revolutionary changes in technology and in laboratory techniques that have sort of garnered an explosion in the utility of luminescence dating, and especially optical luminescence rather than thermal luminescence. And then every month there are more papers coming out of different creative uses of luminescence properties of quartz and feldspar. And so really it's one of these techniques that has really seen a huge expansion in the last 20 years and is continuing to expand its usefulness. At this point, it is an incredibly well-established and common dating technique among quaternary geologists.
So questions asked, and I sort of have this one in my own mind too, is how does this technique compare to Zircon dating? And I guess maybe question would be, is it faster and cheaper? Zircon dating is not trivial.
Yeah, no, I agree. No, it is. Yeah. So as I kind of alluded to earlier, luminescence dating is faster and cheaper, and but also, the dating of zircons, especially for detrital zircon sort of studies now, is so technologically advanced in the last few years that its price is also coming down. So yeah, I think the real distinction is how incredibly precise the uranium lead system is in a mineral like zircon. Whereas this sort of, the luminescence properties of grains being buried and bombarded by radiation has multiple sort of uncertainties and things that we're estimating. And so, yeah, really that's the distinction. It's relatively quick and easy, but also then relatively imprecise. But then we make up for it by just getting more data.
Yeah, so you're talking about uplift. Another question here: uplift with respect to the Yellowstone system, whatever it is, and how do you separate uplift from that versus uplift and/or subsidence in the broader basin and range system?
Yeah, I think so. I think that is a very difficult thing to do, because really what we're going to look at is a data set that tries to quantify the rates and patterns of river incision. And then we're going from those rates and patterns of river incision to tectonic interpretations. And so there's definitely a step, and you'll see that my conclusions here are pretty arm wavy. But hopefully that conceptual model, right, if we think about these end member patterns of what would we expect to see if we have upstream uplift versus downstream base level fall versus faults, chunking them up. Hopefully those three sort of end members can help us answer that question of what control is it that we're looking at.
Okay. Do you want to save, they're sort of tapering off at the moment. You want to save the rest until the end?
Yeah. It seems like some of them are kind of getting at like what I'm about to show you. So, so I'll actually get into the results here and reshare my screen. Get it in presentation mode and get my laser pointer going again. All right. Okay, so here's a very complicated map of kind of zooming in on this study area. And so the white lines here are rivers. And I want to point out here, so here's the Snake River coming out of Jackson Hole towards Hoback Junction. And then here's the lower Hoback River coming out of the Hoback Canyon, going past Camp Davis at its confluence. And then here is where we go past Astoria. We go past this big, broad, braided reach that you guys, I'm sure, are familiar with as you drive towards Alpine Canyon. And then the highway and the river turns to the west, and it punches through the Snake River Range, through Alpine Canyon, down to the town of Alpine and Palisades Reservoir. So the bright colors here, of course, are from a geologic map that we don't have labeled too much. But one thing you'll note is that there are these old fold and thrust belts, severe age reverse faults or thrust faults that offset Paleozoic rocks from Mesozoic rocks in green. And then, another of these severe age thrusts here. But also in the landscape, there are normal faults. And so the Hoback fault is this black traced line here. And as far as I can tell, if you look at the USGS, for example, fault and fold database, this Hoback fault, there's not much information on it. And it's not really clear how active or if this fault has been active in the late Quaternary. We'll talk about this Astoria fault zone, which does not actually appear on any existing published maps, but there is a normal fault here that one can see as you drive on the highway that actually offsets these Quaternary gravels that we're looking at. And then there's the Grand Valley the Grand Valley Fault Zone or system forming the Snake River mountain front near Alpine. And so these three normal faults are going to be faults that I'll talk about and that we'll think about. Okay, so I want to point out this student who did a master's thesis with me a few years ago had a lot of data and multiple data sets, and I'm only going to talk about a couple of them. One of the things that we're seeing here also are some yellow and nice orange units. One of the things she did is she created a map of quaternary deposits along the river through Alpine Canyon. And so we did quaternary geologic mapping, and then we did surveying of those map deposits and of the modern river, actually. She spent time actually measuring in the field the compressive strength and the fracturing of bedrock to try to get at how strong bedrock is and what its control might be in topography. She did a numeric channel steepness analysis in GIS, which I'm not going to show you the results of. And she had a chapter in her thesis about bedload sediment transport and identifying the threshold where the river goes from a bedrock river to a big braided alluvial river and then back to a bedrock river. Okay, so hopefully this is an introduction to the complicated geology and the setting as we're going through this canyon. Okay, so going from upstream to downstream, I'm going to show you three sets of these, and here's two. So if we're up in the upper bedrock canyon, and in this case, we're talking about around Hoback Junction. Right, so if you're around Hoback Junction, sort of like that last photograph I showed you, you can see that the landscape is dominated by what we call this terrace number 2 that is lying on Cretaceous bedrock above the river. In a cross-sectional diagram, with survey data, these reaches are really dominated by this one terrace that dates from about 25,000 years ago to about 12,000 years ago. Right, so these numbers this is 11.6 thousand years old, plus or minus 1.2 thousand years. And you'll note that this coincides with approximately the last glacial maximum. So this is when there were Pinedale-aged glaciers covering much of Yellowstone and coming down into Jackson Hole. And there's this terrace that dominates this bedrock canyon there. And then there's been incision since these deposits were formed down to where the river is today. Okay, if we take a notch down, this is a photograph looking south over Astoria Hot Springs, or what used to be Astoria Hot Springs, right? And now you can cross this nice bridge and there's a new big development around here. This photograph doesn't do much justice, but the highway heads off this way and you enter this big braided reach where there's always people fly fishing off of boats. But this big tall deposit that I'm standing on is a huge alluvial river gravel of sediment that seemed to have filled this huge valley at a prior time. And it's older than this terrace 2 up here. We call it terrace number 3. Okay, so here is a cross section from this area, kind of going from the left side of the river down across where Astoria Hot Springs is, and then up onto where I've taken this photograph looking to the south that you see over here. And instead of having only this one main terrace from the last glacial maximum, in this landscape, this terrace is hard to find at all. And instead, there's this huge, thick river gravel that is older in age, this T3, and it's up to 80 meters thick. And one of the things that I found really a bummer, when we first came to this landscape, I thought, oh, this is great. We're going to have a somewhat older river gravel here, and then we're going to have a really old, high river gravel here. But when we got our numeric age results back, this might be what somebody observed before. The ages here are actually older, right? This is 90,000 years old, taken from, right over here on this photograph. And then this higher upper gravel is actually a little bit younger. It's like 75,000 years old. And then it gets really complicated because some of this higher gravel is offset by the Astoria Fault, this sort of unmapped fault. Excuse me. And so don't worry about this age. This age is interpreted as actually being in the downdropped footwall. No, the downdropped hanging wall, sorry, of this normal fault. And that's why we have this younger age here. So at first we thought, oh, this is going to be older because it's higher, and this is going to be younger, and this will be youngest. But in fact, this is the oldest, and this is a little bit younger. And the only way to interpret this that we can come up with is that, in fact, these two gravels across the valley from each other are actually a part of the original gravel. There was one single original gravel. So if we could reconstruct before erosion the bottom of this gravel deposit, we would maybe connect the bottom here. And we could suggest that at some point about 100,000 years ago, the Snake River here began aggrading and depositing this thick gravel. And it continued past 75,000 years ago, way up to here, before it turned around and incised. And then, just to fool with geologists, as the river incised, it must have stopped and planed off the top of this terrace, just to try to fool me. And then it continued incising back to where it is today. I'm sorry, that was maybe unnecessarily complicated, but the main terrace deposits are this terrace number 2 from the last glacial maximum, and then a very thick alluvial deposit that dates from 100,000 years ago to younger than 70,000 years ago. Okay, so this is in the upper canyon, headed into that big braided reach as you enter Alpine Canyon. And then if you're in Alpine Canyon and near the mouth of it, this is what the stratigraphy looks like. We have both this terrace number 2 that's younger and this terrace number 3 that's older. And but this terrace number 2 now is perched relatively high above the modern river. Right, so this photograph that was also my title slide shows the Snake River coming out towards us through the Narrows. And this is a picture taken when the Palisades Reservoir was at a very low elevation, right? And so a lot of times, if you are in this area, the reservoir is very high and it actually backfloods the mouth of Alpine Canyon and covers this incredible narrow gorge at the mouth of the canyon. And so this is there, and you can see there's been a lot of bedrock incision since the last glacial maximum left behind this T2 deposit. And then this older T3 deposit here, if we turn around in this photograph and we're in Alpine, outside, just downstream from the mouth of the canyon, this T3 makes up the big terrace that sort of looms over Alpine and has a thick lust cap on it. And our OSL ages from this are 75 and 70,000 years old. Okay, so I think these diagrams, if you're not used to looking at them, may be kind of difficult to decipher. And this one might be even harder. If we go to the area of the lower part of Alpine Canyon and around the town of Alpine, we can take this dated, surveyed terrace data of where the river was in the past and convert it into a little plot like this. And the black line here is actually supposed to represent the elevation of the riverbed through time, going from about 100,000 years ago towards the present day. Right, so if we try to reconstruct the elevation of the river through time, we would say, well, back here at 100,000 years ago, the river started aggrading and leaving behind deposits and rising in the landscape as this thick T3 deposit was formed. And then at some point here, after 65,000 years ago, the river must have turned around and started to incise through its own sediment, and then it cut through some bedrock. And then at some point before 25,000 years ago, it turned around, aggraded again, stored some bed sediment, and left behind our T2 deposit. And then after the last glacial maximum, the river has cut dramatically down to where it is today. So I'm sorry, this is sort of a history of the river and its elevation through time, and it goes up and down, and that up and down relates to cycles driven by climate change. And as climate changes, glaciation in the headwaters and the balance between discharge and sediment load, it creates these terraces. Okay, but here's the important part. If these are markers of where the river used to be in the past, depending upon what data points we use and how we connect them, we can make lines like this that actually give us the rate at which incision is happening overall in the landscape. So if we try to have a trend line through the history recorded by these terraces, this is what we get. So this is one place. If we go to the other places through the canyon where we have survey data and geochronology data, in general, through Alpine Canyon and in this part of the Snake River, we can take a step back and say that the overall incision rate through the landscape here is something like 300 meters per million years, right? And that's, that's sort of trying to see through the noise of how the river rises and falls with climate. Right, so I'm trying to get at this background trend and ignore a little bit these rise and falls with climate. All right, so 300 meters per million years, what is that? That's a healthy rate. That is, there have been some preliminary studies done on the leading edge of Yellowstone that have rates maybe similar to that, but most rates in the Western US are half this. And so this is consistent with an area where there's quite a bit of base level fall, and where incision through a canyon like this is happening relatively quickly. The title of this talk related to the history and the age of Alpine Canyon. And so before I forget, if we made what is probably a terrible assumption, and we assumed that this rate is something measured over the last 100,000 years. If we assume that that rate continued farther back in time, we could ask the question, well, how long would it take to cut all of Alpine Canyon? Well, in fact, Alpine Canyon is, give or take a bit, it's about 1 kilometer deep, right? It's 350 meters deep. So in general, if you're driving through Alpine Canyon, here is a quick back of the envelope guess. And that is Alpine Canyon has taken maybe 3 million years to cut, right? At this rate, the Snake River would cut through the mountains and create the entire relief of Alpine Canyon over approximately the length of the Quaternary. That's actually sort of an interesting result, or maybe it's just a coincidence. There are detrital zircon studies done by Paul Link and his colleagues and his students that suggest that the Snake River, maybe the upper Snake River through this part of the world, maybe was captured and joined the trunk Snake River in the Snake River Plain, maybe 2 or 2.5 million years ago. So in fact, the river may be 2 or 3 million years old here, and maybe it took 2 or 3 million years to cut this canyon. Okay, here's another little bit of an unfun diagram. So this is another long profile. The black line here is the Snake River's elevation going from upstream to downstream. And in fact, this line is the Hoback River coming out of Hoback Canyon, coming again to the confluence at Hoback Junction. And then the Snake River as it comes towards Alpine and goes through Alpine Canyon. All right, so this is the upper bedrock reach. Here's where the river turns at Astoria and this Astoria Fault, and it's this big, wide, braided alluvial reach. And then the river again turns to the west, and the lower bedrock canyon is shown here, where it comes out with the narrows. So one thing I want to point out, if you just look at this black line, the river, the Hoback River is a relatively small river, and it's pretty steep. It hits the Snake River, but then as you go through and you go downstream, notice how the Snake River, the gradient of this river is actually increasing. And especially here, right near the mouth of the canyon, the gradient noticeably increases in this Nick zone. All right, so a Nick zone is just a reach of sort of anomalous steepness, right? As a river goes downstream, if anything, it is supposed to get less steep as you go downstream. But the Snake River actually gets steeper towards the mouth of Alpine Canyon. We're going to talk in a minute about how the Hoback Fault, the Astoria Fault, and potentially the Grand Valley Fault play a role in these markers. The other thing I want to show you is these black dots are all kind of intense survey transects done through these river terraces. And specifically, these black dots show the height relative to the Snake River of the basal bedrock contact of this T2 terrace or gravel. Right, so the T2 strath has been measured in all of these black dots. And then with the dashed line, we've connected them and tried to correlate them from one place to another through mapping and surveying. And so this dashed line is a 20,000-year-old marker, right? It marks where was the river 25,000 years ago, let's say, compared to where it is today. So one thing I want to point out is that this 25,000-year-old marker is pretty high above the river, but it hits this fault and it disappears and it goes below the river grade. It then reappears and stays pretty high towards Hoback Junction. Here, when we get to the Astoria Fault and we get into the alluvial reach, we lose this landform entirely again. And potentially that's because it's actually below the modern river. Eventually that emerges again, and the terrace is at a moderate height in upper Alpine Canyon. But then this T2 Strath Terrace, this 25,000-year-old marker, as you go towards the mouth of the river, gets higher and higher and higher relatively. And it peaks right here in the Narrows at the head of Palisades Reservoir. So if we were to calculate an incision rate through here, we would say, well, here's a pretty high incision in the last 25,000 years. This is an area where there's no incision at all. And then here's an area where incision rates get faster and faster and faster as we get to the mouth of this canyon. Okay, so pausing really quick. Here are some things that I think we know so far. First of all, I tried to report to you that there's a healthy incision rate in general across this landscape of something like 300 meters per million years. But that incision rate, depending upon where you are, is going to be different depending upon if you're near a fault or if you're at the mouth of this canyon or the head of this canyon. Also, if you remember that conceptual model, one thing that this terrace does not do as we surveyed is it doesn't do any sort of simple sort of thing where it converges downstream. So remember, one of our options was that the terraces would go from higher here to lower here. And it's not that simple, right? The terraces are high and then they disappear. And then they're kind of low and then they get really high down here. And then finally, one thing that you can see already is that we're going to have a story where these terrace markers are being offset by faults that must be active in the Lake Quaternary. And that faulting controls the main pattern that we can see as we go out and map and try to date these terraces. Okay, so here again is this slide I'm repeating. As we go from upstream to downstream along the Snake River, we were just sort of zoomed in on this reach in Alpine Canyon and around Hoback Junction. I've got two more slides where I just want to take you up to the mouth of Hoback Canyon here and show you some relationships there. And then I've got one quick slide to show you a couple of ages and some relationships down here close to where the river enters the Snake River Plain. Okay, so first let's go up here to Hoback Canyon. And actually what I want to show you is the Hoback Fold. So I bet a lot of you are familiar with the Hoback Fold as it heads south from the Jackson Hole area. And it runs, north-south across the mouth of Hoback Canyon. So this is the highway, and this picture is taken looking south. If you were driving to the east and going and about to enter Hoback Canyon, this would be the highway you would pass here. And this right here is a backpack, or maybe even it's a graduate student slumped over a sample location where we're getting a luminescence sample. And that luminescence sample came back at about 21,000 years old. All right, so the next time you drive past here, if you look at this road cut, one of the great things about road cuts is they provide exposures for geologists. And we have a date. The gravel that's deposited here is from the Hoback River, but the Hoback River's bed was up here at this height above the highway at 21,000 years ago. And then today, if you go left off of this road today, you can hike down through sort of a camping or picnic area and get to the Hoback River, which is at least 10 meters below the highway here. Sorry, I didn't mean for this text to come up yet. Ignore that. So here, that road cut that I just showed this picture of, that is here. This is a photograph looking south across the mouth of Hoback Canyon. The Hoback River is flowing from right to left, and we can't see it because we're standing on these terraces that are higher, and the river is stuck down there And these trees are growing on the higher floodplain levels. So the main thing I want to show you is that as the Hoback River comes out of this canyon, the valley broadens and you preserve these nice terrace landforms. And so I'm standing on a higher terrace. This is that terrace that has got a little bit lower top to it. Then you'll notice there's this conspicuous north-south scarp here that is at a 90-degree angle to the trend of the river. And then here's another terrace level here. And here's how we interpret that. This is the trace of the Hoback Fault. And if we presume that this terrace landform top is the same as this terrace landform top, and that it formed 20 or 15,000 years ago, then I'm going to suggest that this is a fault scarp, and that the offset of this landform along this fault scarp is about 3.5 meters. All right, so the Hoback fault here, in my interpretation, has offset this terrace landform by 3.5 meters. And we know the age of this landform very roughly. And so there's kind of a long discussion in this paper that's in press, but the take-home message is that if we use the ages of our terrace 2 and this offset since it was formed, you can get a general range of possible offset rates of about 1/4 to 1/2 of a meter per 1,000 years. This is the rate of slip of the Hoback Fault over the past about 15,000 years. That converts in the units I was using earlier, that converts to 250 to 500 meters per million years of fault slip. So to my knowledge, these are the first constraints on any late Quaternary activity on the Hoback Fault. So I think this is sort of neat. It needs a lot more study, and this is very ballpark. But I believe it shows that this fault is indeed active in the late Quaternary. And these are the sort of range of rates that it's active at. Okay, now remember that was upstream. We're going way downstream. And so the South Fork Canyon of the Snake River is coming towards us here. And behind me, if I turned around from this wayside rest and took a photo looking the other way, it would look out over the Snake River plain downstream. All right, so the river here has a very fascinating history that's only begun to be studied by a few folks at BYU, Idaho, and other places. But maybe some of you know this. There are young Quaternary basalt flows that fill in the Swan Lake Valley in this area. And those basalts in places bury river gravels that people have interpreted as Paleo Snake River gravels. Okay, that's a good example of me getting diverted. But since this time, the Snake River here has also incised. And if you get luminescence ages from these lowest terraces in the landscape, we've got a luminescence age of about 50,000 years old on this gravel here, and then about 25,000 years ago, the T2 on this gravel here. One of the things about these gravels is that you never see the bottom of the gravel. These are thicker deposits, and any bedrock that's at the bottom of this is still below the modern river grade. All right, so even though there are some late Quaternary ages, we don't actually see the bedrock underneath them. And effectively, the incision rate here is sort of like 0. The bedrock incision rate of the river here is very, very low. And for example, this 1 to 2 million year old basin fill, or I'm sorry, this 1 to 2 million year old lava flow is in the sort of same landscape position as the 90 or 70,000 year old gravel way upstream in Alpine Canyon. So what I'm trying to get at here is these couple of initial ages looking at terraces here very roughly confirm that as the Snake River is going downstream and entering the Snake River plain, its late Quaternary incision rates are getting very, very low and approaching 0. Okay, so I'm at my kind of conclusion slides here. If we look at these terraces as markers in red across a profile of the Hoback and Snake River going from the Yellowstone crescent of high terrain to the Snake River plain, one of the things it does is it clearly crosses a bunch of normal faults. And some of these normal faults are not even mapped or were not known to be active, but they are clearly active in the late Quaternary. So one thing we can confirm is that these faults definitely do affect these terraces and that they're active. Another thing we can see is that this red line does not really appear, it does not really converge downstream. And instead, the highest incision is right here, kind of in the middle of this profile at the mouth of Alpine Canyon. Then we lose everything underneath Palisades Reservoir. And the river runs along the strike of, the Graben through Swan Valley. And then down here, right before it enters the Snake River Plain, we see that any sort of 20,000-year-old, 25,000-year-old bedrock strath is actually below the river level. And that in fact, incision rates here are essentially 0. So what is this view? How does this relate to our kind of conceptual models here? Okay, so if you guys have been following me, I'm trying to tell you that we do not see this, right? We do not see terraces converging downstream way up here. And instead, one thing we definitely see is we see these terraces being offset by faults, right? This pattern we definitely see here. And if anything, there is some downstream subsidence that seems to be driving incision. And this incision might be propagating upstream, giving us things like steep nick zones, which we see here at the mouth of Alpine Canyon. All right, so it's a little bit unsatisfying, but this study initially says, well, we don't really see this signature of actual uplift along this crescent of high terrain. We do definitely see active faulting. And then this, the paper has other lines of evidence from terrain analysis that also sort of lean towards this. If it's, if it's either uplift upstream or subsidence downstream, I would argue that the incision of this landscape is mostly driven by subsidence downstream and then complicated by faulting, offsetting it. Okay, this is my last slide, and then I've just got some take-home points. I captured this image off of Google Earth just about 2 hours ago and plopped it on as my last slide. This here is the Snake River coming out of Alpine Canyon and coming into Alpine, Wyoming, right? This is where the Grays River joins it, and you can see Palisades Reservoir here. So this is the mountain front of the Snake River Range going off to the north. And one thing I want to point out is that there has been mapping, but nothing recent, of the main fault system that runs through this area, which is the Grand Valley Fault. And the Grand Valley Fault comes out here from being very active to the south here, and with clear fault scarps and stuff like that. It hits a segment boundary where it drops off here, and then it must be picking up again somewhere here. And one strand of it is mapped here. And if you look at, there are these beautiful, especially here, these triangular facets and what looks like a tectonically active mountain front, and sort of suspicious lineations in the landscape. If you look at prior studies, people have suggested that this Grand Valley fault system here at the mouth of the canyon, that there is no evidence that it's been active in the late Quaternary. But going back to, I don't want to do this too far, but going back to our observations of very fast incision, a bedrock nick zone right at the mouth of the canyon, and patterns telling us that there is sort of downstream base level fall occurring. I guess my statement is that in addition to subsidence of the Snake River Plain, one of the main potential drivers of incision in Alpine Canyon might be that the Grand Valley fault system here is actually more active than we previously thought, and that Alpine here in the basin may actually be down dropping, and that this fault might be slipping and more active. Otherwise, to me, it becomes very difficult to explain this relatively impressive and extraordinary nick zone right at the mouth of the canyon here. Okay, last slide. We know that over this region in general, on average, it looks like incision rates along the Snake River are really nice, healthy 300 meters per million years, and they peak right here at the mouth of Alpine Canyon. Terraces do not converge downstream, and instead, those terraces are offset by local normal faults. The Hoback Fault, we can say, has definitely been active. The Astoria Fault exists, and in fact, I would suggest that it's possible that this Grand Valley Fault might be more active than geologists might have previously interpreted, sorry. Then finally, our initial data from farther downstream suggests that, yeah, incision in fact declines to about 0 as you approach the Snake River plain. And then overall, then this sort of intermediate time scale quaternary picture is one where, well, base level fall downstream, either from the Snake River plain or from local faults, seems to be driving the erosion and incision in the landscape. And our data did not really support that uplift of this Yellowstone crescent of high terrain is the main driver of erosion in the landscape. All right, that's my last slide. And I appreciate you guys holding on for the second half of that and some of those sort of unlovely diagrams from this paper.
Thank you very much, Joel. Really, from my perspective at least, exceedingly interesting. And there are some questions. And I guess the simple one, you basically answered it, I think, is basically there's it's best as yours and your students' data would answer the question. There really is not a visible effect of the Yellowstone system on what's happening currently in that Snake River Canyon.
Yep. I think that our, I want to be tentative, and this is the kind of the first sort of more data-rich study at this time scale along a river. But yeah, I agree. And I think this paper went through a review at the journal, and I guess I got the sense from the reviewers who know more about the Yellowstone region than I do probably, that that kind of Yellowstone crescent of high terrain really is sort of hypothetical. that it's a concept that there so far isn't there aren't a lot of measurements that there are no measurements in the landscape that show us that is a real feature of active uplift.
Okay, here's another good one. And the question is, why do we form terraces? Is it climate? The 20,000-year-old terrace correlates to the end of the Pinedale. 90 to 60 K is not matched to clear advance of the Yellowstone ice cap. Actually, it's after the Bull Lake, which ended about 130,000 years ago. So you're in an interglacial when a lot of those terraces are forming, not at the onset of or the end of a glacial epoch. So how come?
Great. I absolutely have intentionally left the discussion and any figures related to how does climate work to give us these terraces and control what rivers do over time. And it is a wonderful and complicated subject. And I guess I think even though the Snake River through Alpine Canyon is downstream of any direct glaciation, it is clearly in a pro-glacial setting. And in fact, you just mentioned the Bull Lake moraines, which remember are south of Jackson, they actually sort of loom high in the landscape above and just to the north of Hoback Junction. And so we are right here where the glaciers were ending as they came and go in the Quaternary. And those glaciers had enormous effects on the water and sediment balance in these rivers. So climate, as it changes river behavior, and it leaves behind these terraces. And then there's this conundrum. Well, we have a terrace that belongs to the lake glacial maximum, but then there's this incredibly thick deposit that is in this sort of what we sometimes think of as an in-between time from 90 to 60,000 years ago. And so one thing I don't have to share with you, but I should, is I think that I still feel really comfortable with this because, in fact, even though in our Western landscape, we tend to only preserve the Bull Lake glaciation and then the Pinedale glaciation, there is another glaciation that is in between those two, right? And those of you who've done quaternary geology know that there's isotope stages, right? So the Bull Lake is isotope stage 6. And then there's an interglacial during isotope stage 5, which is a very in-between time, climate-wise. And then there's isotope stage 4 from about 75 to 60,000 years ago. And in other places in the world, isotope stage 4 is another glaciation. And then we have an interglacial before we have the onset of the Pinedale glaciation. So something I want to remind people, our record of glacial deposits and glacial moraines preserves and only shows us the Bull Lake and the Pinedale. And that glacial record is incomplete in the 100,000 years in between those two. And I guess I'm here to tell you that I believe there was ice and that there was some glaciation during that time. And that in fact, part of this big thick terrace gravel that is our T3 that we dated does date to isotope stage 4. And all that means is that that ice, if there was ice on the Yellowstone region or in Jackson Hole, that it must have not been as large as the Pinedale glaciation, right? It could have been only slightly smaller than the Pinedale glaciation. And then the 25,000 years ago, the Pinedale glaciation comes, totally wipes out all of the glacial evidence of that. But what's still left behind are these river terraces downstream. So of course, I'm a fan of river terraces, but one of the great things that river terraces offer is a more complete record through time of our quaternary history, because the glacial record is really incomplete. It gets blown out every time the next biggest glacier comes and wipes out everything in its pathway. Sorry for that long answer.
No, not at all. Ben Crosby just asked a question that I had written down for myself, and that is, what's the chance that landslides and damming of the Snake River could affect the interpretation of terraces in the canyon?
Yeah, excellent. As many of you, I'm sure, know or you've observed, and we know from history, right, and from road construction, Alpine Canyon is riddled with not only landslides, but debris flows and et cetera. And so in our mapping and in our analysis of bedrock controls on the steepness of drainages, one of the things that we can say is that those landslides tend to be focused in the Cretaceous rocks with shales, and that the landscape is just completely riddled with it. One of the good things, though, is that there are places where our T3 and our T2 are basically wiped out and deformed by subsequent landsliding. But in most places, they're not. And so I'll just admit that as we were looking at and mapping these older quaternary terraces, I feel confident that we were able to kind of piece together the paleo long profile of the river by sort of avoiding places where it clearly had been landslid around. I think another thing, though, that Ben's question brings up at the intended is that when you have a big landslide like that, it will dam a river or back it up or contribute bed load to the river and coarsen its bed and steepen it. And one of the things that was a conclusion of our study is that when you get into the tributaries of the Snake River throughout Alpine Canyon, those tributaries are very much controlled by landslides and changes in bedrock. And they have nick points here and there, and those nick points are hung up on landslides. But when you get to the main Snake River, the main Snake River apparently appears to be powerful enough that it sort of regrades and punches through any landslides. And I think what we're looking at is that the river there is easily gets through those landslides, and at the longer markers we're looking at, they themselves are not affected over longer timescales by landsliding. Sorry, I hope that was a clear answer.
Yeah, oh, well, it was for me at least. And yeah, those most of the landslides, or, debris deposits are pretty ephemeral. I think the Cretaceous sediments are pretty ephemeral. Question here about could you maybe, are you able to make a comparison between the incision rates along the Snake River versus the Colorado and the Grand Canyon?
Oh yeah. Yeah, actually the range of incision rates is sort of similar. And I think for decades, we have sort of used, I think, as a rule of thumb, because of a paper based on Lava Creek B ashes across the West that was written by Meredith Reheis and others. In general, across the Western US, incision rates in most places are maybe on average 115 meters per million years. And so if we zoom in on Alpine Canyon, we're talking incision rates that are twice that sort of normal rate. And the other place in the Western US that I think we know has an anomalously fast incision rate are places in the Colorado Plateau. And I guess one thing that I have studied that is maybe not intuitive is that on the Colorado River and its pathway through the southwestern US, the Colorado River actually has its fastest incision rates right around Moab, Utah. And the incision rates of the Colorado River are actually slower in Grand Canyon. And in fact, as you go through Grand Canyon and you think about Pleistocene timescales, the incision rates get slower and slower and slower through Grand Canyon. So Grand Canyon, even though it is so impressive, actually has relatively slow incision rates. And in fact, Alpine Canyon of the Snake River is in general eroding faster than Grand Canyon is in the late Pleistocene.
Okay, one of your slides actually showed this, but the question came up anyway as to where was the Yellowstone hotspot in that roughly 3 million year ago time zone when you talked about initiation perhaps of the current Snake River that we know.
Yeah, and I'll say, let me think, you guys will have to remember with me. If we go back to that slide with the caldera complexes, right, the Heisei volcanic center was active 4 million years ago, and maybe there's at least basaltic volcanism.
Yeah, just west of Rexburg.
Yeah, that is early Pleistocene there. But then, right, we hop over to the Huckleberry Ridge, sort of caldera at, I'm sorry, you guys remind me, is the Huckleberry Ridge 2 million years or 1 million years old?
2.5.
2.5. So yeah, so somewhere in between, Rexburg and up by Island Park is where the hotspot, must have been about that time.
Okay, well, Ben said 2.1. I think it's more closer to 2.4, but we can argue about that. Let me ask and comment, I guess. I've always been troubled and disagree with USGS interpretation of the Hoback normal fault. They basically say it's dead, and they say pretty much the same thing for the Swan Valley system. And I guess I'm just pleased to see that your data strongly dispute that, because the Hoback normal fault is basically the southern extension of the Teton fault. Divergence changes along Highway 22, but it's the same fault system. So I've always been troubled by that. So I think it's really neat, and I think really important to see the data you have there at the mouth of the Hoback Canyon.
Yeah, I think we have so little data there, but I think, it's just enough to justify somebody going and really checking that and looking at that fault scarp for sure.
Yeah, well, you can see those facets, along that face of, where the Hoback normal fault is very, very clearly. But I really wasn't aware, and certainly it's really interesting to see the evidence for motion on that Astoria fault.
Yeah, I don't know if it's sort of a dangerous outcrop, but if you guys are driving to the west past Astoria, right on the right there, there are these high gravels that loom above you. And if you're able to get out and kind of crawl around up there, you can see this fault. And so anyhow, I think, for both the fault scarp at the mouth of Hoback Canyon and that Astoria fault that offsets the gravels in outcrop, one thing that I guess I knew is that in talking to other professors who lead field camp projects in that area out of Camp Davis and elsewhere, they all know about those things. So even though they may not appear on published maps, if you ask people who have led field camp projects around there, they're like, yeah, there's this fault that offsets the Pleistocene gravels. And there's this fault scarp at the mouth of the canyon.
Well, another question that's been posed is what further study or research do you and your students have planned for this area?
One thing, I do have hopes and plans for further research, but not necessarily along the Snake River. One thing is that I'm really spoiled. I do most of my work in the Colorado Plateau, where there are perfect exposures, and Alpine Canyon is so beautiful, and the Snake River is very, very beautiful, and I love to boat. But there's too much trees. There's way too much vegetation, and the outcrops are not good enough. So it's kind of slim pickings. I do want to, just a quick pitch though, I do have there's another drainage system that might be ideal for this kind of a study. And we do have a proposal in to work specifically along the Gallatin River. The Gallatin River runs north, of course, and eventually goes past Bozeman. And one of the advantages of the Gallatin River is that it flows directly off of the Yellowstone Plateau, but its headwaters were not intensely glaciated or covered by the Yellowstone ice cap. And so anyhow, maybe the second and last study that I'll get to do will be along the Gallatin River, where it might be a better sort of field laboratory to test whether terraces are tilted or not.
I don't know, this may be a last question, and you may have answered it in your discussion. What kind of age would you put on the inception of the Teton fault system, which includes, of course, the Hoback normal fault system, and why?
Well, I can definitively and proudly say, I do not know. That's a question for somebody else. And Ben Crosby has asked a question. I'm sure he'll have a better idea. And his colleague at Idaho State, Glenn Thackeray, has been doing studies, of course, of the Teton fault. And if I had a better memory, I could just sort of repeat what I've learned from Glenn Thackeray, but I can't remember. I'm sorry.
Have you looked at the Ken Pierce and Joe Licciardi paper on the glaciation, which there's a page in there that pretty definitively suggests or states that the Teton fault has to be younger than, say, 4.1, 4.2 million years of age.
Okay, well, excellent. So the newer Licciardi and Pierce paper I have not read very carefully. So, but clearly they are using they're using markers and geologic data points and piercing points that are older than river terraces.
They are, but there's a pretty good constraint. I think it's actually on page 9 of that paper, if I recall correctly. I'd have to go back and look, but it's a pretty prominent interpretation based on some pretty compelling data. Yeah,
well, that is an interestingly old age, considering the place seems to be overrun then by the Yellowstone hotspot now.
Yeah, and there's a question. There are interpretations of much older ages for the onset of the Teton fault system. So it's definitely still an open question, but I really think that Licciardi and Kent Pierce paper of about 3 years ago has a pretty compelling story in it.
Excellent.
I don't see that Ben, I don't know if Ben's still on, but he's not commenting, so I don't know what he thinks. I'll have to ask him later. I don't have any other questions. Do you have any final comments? I mean, there's been some comments. really appreciate the presentation. Really interesting and compelling. It's nice to see real-time data, if you will, and interpretations, and to see, have somebody walk us through what it means.
Awesome. No, thank you all for listening. It's always wonderful to get to share this stuff.
So, we regret not being able to have you here in person. So maybe we'll have to drag you back when we can do things live and have you come up and visit us.
Yeah, excellent. And I'll just come up and visit and attend anyhow when we're all done with this stuff.
One last question. Ben wants to know what was learned from rock hardness measurements. That's an easy one.
I mean, I guess actually maybe there is a quick take home. One of the things we learned is we learned two things. First of all, the steep local tributaries in Alpine Canyon that feed debris flows and stuff. If you look at those drainages and try to see a signature of any tectonics in them, that signature is lost or cannot be deciphered from bedrock. And so between landsliding and the changing hardness of Paleozoic limestones versus Cretaceous shales, the local tributaries are totally dominated. Their topography is dominated by bedrock and changes in bedrock. And then the second one is the mouth of Alpine Canyon. As you drive down Alpine Canyon, the river gets steeper and steeper and steeper as you go through the whitewater all the way to the mouth. And that steepening of the Snake River through Alpine Canyon, that steepening itself cannot be explained by bedrock, right? The middle part of Alpine Canyon is in the same Paleozoic limestones as the very mouth, not the exact same, but the Paleozoic limestones at the very mouth of the canyon where it's super steep, and a little bit farther up in the canyon where it's not as steep. They are mechanically the same strength, even though one is Cambrian in age and one is Mississippian. So those are the two take homes. The bedrock cannot explain the Nick zone at the mouth of the canyon, but it dominates the kind of tributary topography of the region.
All right, well, thank you so very much, Joel. A really entertaining, informative presentation. Just want to, thank you. I want to thank everybody for joining us. And I want to remind everybody that we have Sarah Lambert from the University of Utah, who's going to talk about a slightly different type of topic on May 4th, Tuesday. She's going to talk about stuff that we really can't see, which is sort of the whole interior of the Earth. All that stuff below us, for thousands of kilometers. So that should be a really interesting presentation as well. So thank you, Joel, very, very much. Thanks everybody for joining us. Thanks for the questions. And we look forward to seeing you on May 4th. Thanks, Joel, very much.